Here's kind of an old-timey puzzle about numbers. Suppose you've got two numbers which add up to 24. You've got two numbers that sum to 24. How large can their product be? When you take those two numbers that add up to 24, how big of a number can you get when you multiply them together? This is an optimization problem, so let's draw a picture. Okay, maybe I can't draw a picture in this problem, but at least I can label things. So instead of just saying two numbers that sum to 24, let's give them a name. Two numbers x and y, which sum to 24. And instead of just saying how large can their product be, I can say how large can, x times y be. So what's the goal? Well, my goal here is really just to maximize the product. So maximize x times y. And there's a constraint. The constraint is that x and y have to add up to 24. So I'll write that as x plus y equals 24. Rats, xy isn't a function of a single variable. I need to rewrite it so it's a function of x alone. Now, since x plus y is 24, I could rewrite this as y equals 24 minus x, and consequently x times y, which is the thing I'm trying to maximize, I could write that as a function of a single variable, x times, and instead of y, 24 minus x. So this is the quantity now that I want to maximize. Now I can apply calculus. Let's differentiate and then find the critical points. So here's this function of a single variable that I'm trying to maximize. My function is x times 24 minus x. That's really y, right? This is x times y is the thing I'm trying to maximize. But if I expand this out, I get 24x minus x squared. And then I can easily differentiate this. The derivative of this function is, what's the derivative of 24x? Just 24. What's the derivative of minus x squared? It's minus 2x. I'm trying to find critical points, right? Critical points are where the derivative doesn't exist or where the derivative is equal to 0. Now this function is just a polynomial, so it's differentiable everywhere. So I don't have to worry about the function's derivative not existing somewhere, but I do have to find places where the derivative is equal to 0. So when is this thing equal to 0? Well, that's the same as asking when 24 is 2x. That's exactly when x is 12. So here is my critical point. What sort of point is that? Well, let's think about the SIGN, the sign of the first derivative. The derivative is positive if x is less than 12, and the derivative is negative if x is bigger than 12. What does that mean? Well, that means the function's increasing for x values less than 12, and the function's decreasing for x values bigger than 12. So the function goes up, gets to 12, and starts going down. What kind of point does that make 12? Well, that must be a maximum. So I'll write f of 12 is my maximum value. So what do we conclude? So here's our conclusion. 144 is the maximum product of two numbers which sum to 24. Did we really need the awesome power of calculus to solve this problem? No. For example, you could have used a technique like this. There's the so-called arithmetic geometric mean inequality, the AMGM inequality, and what it tells you is the following, that for numbers a and b, the arithmetic mean, it's a fancy word for the average of a and b, is bigger than or equal to the geometric mean, which is the square root of the product of a and b. And this inequality becomes an equality if and only if a and b are the same. Now, how can you use something like this? Well, in our specific case, what do we know? I know that x plus y is equal to 24. And if these two numbers add to 24, then their average, x plus y over 2, must be equal to 12. But if this is their average, by the AMGM inequality, this must be bigger than or equal to the square root of x times y, the geometric mean of x and y. Now, how does this help us? Well, what if I square both sides, right? Then I know that 144 is bigger than or equal to x times y. And that's exactly what I'm trying to figure out. I'm trying to figure out how big can the product of x and y be if I know what the sum is. And what this is telling me is that the product can be no bigger than 144 with equality when x and y are both equal, and that happens when they're both equal to 12. That you don't actually need calculus to solve many of the problems that are assigned in calculus courses is perhaps one of the best kept secrets of calculus instructors. A result like this AM-GM inequality actually solves a ton of optimization problems. You often don't have to resort to taking derivatives if you can just apply a result like this. Calculus is a powerful tool, but there are other ways to attack these problems. Don't be afraid to make use of other methods.